Hello everyone. Today we're going to talk about 13P Atlas because we're entering an absolutely decisive week for this interstellar object. And there's big scientific news. Professor Avi Loeb has calculated the mass of this cosmic visitor using data from the Hubble Space Telescope and the James Webb Space Telescope. How much do you think an interstellar comet weighs? The answer might surprise you. Let's explore these fascinating calculations and find out why this week will be crucial for finally determining the true nature of 13P Atlas. We are living through a historic moment in the observation of 13P Atlas. Tomorrow, September 29, 2025, the object will reach its perihelion, the closest point to the Sun in its orbital path. This marks the moment of maximum thermal and gravitational stress. If 13P Atlas were truly an alien spacecraft, as some have speculated, the intense solar heating would completely strip away any superficial material, revealing an underlying artificial structure. But if, as all scientific evidence indicates, it is indeed a comet, we'll witness a dramatic surge in activity. Solar heating will intensify the sublimation of ices, producing a brighter coma and possibly a more prominent tail. The rate of mass loss will rise sharply, and jets of gas and dust will grow increasingly vigorous. All of these are hallmark cometary behaviors, and we've already begun to observe them. However, the week holds another crucial date, October 3rd. On that day, 13P Atlas will make a close pass by Mars, not a collision, but an astronomically significant approach. And here's where things get truly exciting. Mars is currently surrounded by a fleet of orbiters, each equipped with world-class instruments. The crown jewel among Martian observatories is undoubtedly NASA's Mars Reconnaissance Orbiter, MRO. In orbit since 2006, the MRO carries the HiRISE, the High-Resolution Imaging Science Experiment, arguably the most powerful imaging instrument currently operating beyond Earth's orbit. HiRISE is capable of resolving objects as small as 30 centimeters across on the Martian surface. To put that into perspective, from an orbit hundreds of kilometers high, it can distinguish between a large rock and a rover. This extraordinary resolution is achieved through a 50-centimeter reflecting telescope coupled with extremely sensitive CCD detectors. Now imagine pointing this incredibly powerful instrument not at the Martian surface, but at 13P Atlas during its approach. Mission planners are already working on the necessary orbital maneuvers, calculating the proper exposure times, determining the optimal observation angles, and coordinating with other Martian probes for complementary observations. All of this is happening right now in mission control centers. If everything goes according to plan, HiRISE will capture images of 13P Atlas with a resolution of roughly 30 kilometers per pixel. That may not sound particularly impressive compared to its surface resolution, but consider this. We're talking about high-resolution imaging of an interstellar object in motion, millions of kilometers away. It will be unprecedented. These images will finally settle any lingering ambiguity about the nature of the object. An artificial structure would be unmistakable. We would see regular geometry, artificially smooth surfaces, perhaps even mechanical features. None of that will appear, of course, because 13P Atlas is a comet. Yet the images will yield invaluable scientific data about its shape, rotation, surface activity, and nuclear structure. It's important to properly contextualize Professor Avi Loeb's role in this saga. Loeb is a distinguished astrophysicist and professor at Harvard University with significant contributions across multiple fields of astrophysics. He's known for thinking outside the box and for his willingness to explore unconventional hypotheses, a trait that can be both a strength and a weakness in science. Loeb has never categorically claimed that 13P Atlas is an alien spacecraft, a common misinterpretation of his public remarks. What he has suggested is that, given the object's unusual behavior and our limited understanding of hypothetical extraterrestrial technologies, we should not completely dismiss exotic explanations without proper investigation. This position is scientifically defensible, albeit controversial. Science occasionally advances by considering unlikely possibilities that turn out to be correct. However, Occam's razor reminds us to favor the simplest explanations when they suffice. And in the case of 13P Atlas, natural cometary explanations are more than sufficient. They are overwhelmingly supported by evidence. Loeb has been a valuable scientific contributor to studies of 13P Atlas, conducting rigorous analyses published in peer-reviewed journals. His most recent work, Calculating the Object's Mass, exemplifies this serious, data-driven scientific approach. Before delving into the specific mass calculations, it's important to appreciate just how challenging it is to characterize objects like 13P Atlas. Unlike comets within our solar system that can be observed repeatedly over multiple returns, interstellar visitors offer only a single opportunity for study. They appear, make their one-time passage through the inner solar system, and then depart forever. Determining the physical size of a comet is surprisingly difficult. The solid nucleus, the actual dirty snowball, is typically very small and extremely dark, reflecting only a few % of the sunlight that hits it. When it's far from the sun, it's almost invisible. When it moves closer, it becomes completely obscured by the bright coma, the temporary atmosphere of gas and dust that envelops the nucleus. Space telescopes like Hubble and James Webb provide crucial advantages. Hubble, operating in optical and ultraviolet wavelengths, can resolve fine spatial structures with a clarity impossible for ground-based telescopes affected by atmospheric turbulence. The James Webb Space Telescope, working in the infrared, can see through dust and reveal thermal structures invisible in visible light. Both telescopes have observed 13P Atlas. Hubble captured direct images showing the coma and jet structures, while Webb performed detailed spectroscopy, identifying specific molecular species being released through sublimation. These complementary observations have provided essential constraints on the possible size of the nucleus. Based on data from the Hubble and James Webb Space Telescopes, Loeb and his collaborators derived an estimate for the size of 13P Atlas S nucleus, approximately 5 kilometers in diameter. Hubble observations suggest a range between 3.2 and 5.6 kilometers, with 5 kilometers representing a reasonable central estimate. With size in hand, calculating mass requires an assumption about density. Here we enter more speculative territory, but speculation guided by decades of cometary science. Comets are not solid blocks of ice. They are porous structures, more like compacted snow than solid ice, with substantial voids and minimal mechanical strength. Missions such as Rosetta, which orbited and landed on comet 67P Churyumov-Gerasimenko, directly measured cometary densities. The results were surprising. Only about 0.5 grams per cubic centimeter, half the density of water. This low density reflects the extreme porosity of comet nuclei, which may be 70–80% empty space. Loeb adopted this density value of 0.5 GSAM-CM3 for 13P Atlas, a reasonable choice based on known comets. It's worth noting that this is the density of a natural comet, not an artificial structure. A metallic spacecraft would have a density several times higher. Using cometary density in the calculations already assumes a natural, rather than artificial, nature for the object. With both size and density known, mass follows from simple geometry. Assuming an approximately spherical shape, reasonable for objects dominated by self-gravity, the volume is given by 43PR3. For a radius of 2.5 kilometers, this yields a volume of about 65 cubic kilometers. Multiplying by a density of 0.5 GSAM-3, converted to proper units, results in a mass of approximately 33 billion tons. 33 billion tons, a number both enormous and difficult to truly grasp. Let's put it into perspective with a few comparisons. The Great Pyramid of Giza has a mass of about 6 million tons. 13P Atlas weighs roughly 5,500 Great Pyramids. Or consider that humanity produces around 2 billion tons of steel per year. 13P Atlas contains the equivalent of more than a decade of global steel production. Perhaps even more relevant is the comparison with other known interstellar objects. 1I Oumuamua, the first confirmed interstellar visitor, was estimated to have a mass of only a few million tons, 4 orders of magnitude smaller than 13P Atlas. 2I Borisov, the second visitor and clearly cometary in nature, had an estimated mass of a few billion tons, still significantly less than 13P Atlas. 13P Atlas is therefore by far the most massive interstellar object ever detected. This distinction is not surprising. Larger objects are brighter and easier to detect across vast interstellar distances. Observational selection bias naturally favors the discovery of larger objects. As our telescopes and survey techniques continue to improve, we can expect to detect progressively smaller interstellar visitors in the future. Another crucial aspect of Loeb S analysis involves non-gravitational acceleration, deviations from the purely gravitational motion expected for solar system bodies. As objects move through the solar system, their trajectories are governed primarily by the gravity of the Sun, planets, and other bodies. These gravitational forces are predictable and can be calculated with extreme precision. However, active comets experience additional forces. When jets of gas vent from one side of the nucleus, they exert a reaction force that pushes the comet in the opposite direction, essentially the rocket principle operating on a cometary scale. These non-gravitational accelerations can measurably alter a comet's trajectory over months of observation. Oumuamua famously exhibited a significant non-gravitational acceleration, one of the factors that led Loeb to speculate about a possible artificial origin. A light sail, for instance, could in theory produce a similar effect through radiation pressure. In contrast, 13P Atlas shows only very modest non-gravitational acceleration, fully consistent with natural cometary outgassing and inconsistent with any form of artificial propulsion. A spacecraft capable of self-propulsion would display far greater and likely non-radial accelerations. The observational data simply do not support a spacecraft interpretation. It is worth emphasizing again that the use of a density of 0.5 GCM3 in the mass calculations is based on direct measurements of real comets within our solar system. This choice already assumes a cometary nature for the object. If 13P Atlas were an artificial structure, its density would be entirely different. Spacecraft built from materials similar to ours, aluminum alloys, carbon composites, steels, have densities ranging from 2 to 8 GCM3, depending on their internal structure and fraction of empty volume. Even a highly porous structure like the International Space Station has an average density far higher than 0.5 GCM3. Thus, using a cometary density and obtaining results consistent with the observed behavior provides yet another confirmation of a natural cometary nature. If we were to apply a spacecraft-like density to the same calculations, the predicted mass would be 4 to 16 times larger, and the resulting dynamical behavior would no longer match the observations. This week will definitively settle any remaining questions about the true nature of 13P Atlas. The perihelion passage will reveal whether the object survives intact, as comets routinely do, or displays anomalous behavior inconsistent with a naturally icy composition. The close approach to Mars will provide imagery with enough resolution to clearly distinguish between a natural cometary nucleus and an artificial construct. Science advances through the accumulation of evidence. Each new observation of 13P Atlas has added further support to the natural cometary interpretation. Loeb S mass measurements are simply another piece of this puzzle, a piece that fits perfectly with all the others. When 13P Atlas is finally confirmed beyond any doubt to be a comet, after its perihelion passage and Martian observations, it will be a moment for reflection. How many channels and websites promoting alien spacecraft theories will acknowledge their mistake? How many influencers who profited from sensationalism will admit they were wrong? The answer, unfortunately, is probably very few. But that does not diminish the triumph of science. Through careful observation, rigorous analysis, and intellectual honesty, the scientific community has correctly determined the nature of this extraordinary object. 13P Atlas is a comet, a fascinating visitor from another stellar system, yes, but a natural body governed by the same physical laws that shape the comets of our own solar system. And that fundamentally is even more wonderful than any tale of alien spacecraft. It confirms that planetary formation processes are universal, that cometary chemistry is consistent across the galaxy, and that the laws of physics we discovered studying our small corner of the universe apply everywhere. 13P Atlas is a scientific envoy from another star system, bringing us a profound message that the universe is comprehensible, predictable, and governed by principles we can uncover through rational inquiry.